So hey guys, welcome back to my channel. Hope you are doing extremely well, and this is a very own mass code at this side. Today we are here to solve another POTD, which is count pair sum in matrices, right? Count pair sum in matrices. So let us look what does the problem say as usual, right? So it says that you have provided with two matrices. You have two matrices, matrix 1 and matrix 2, right? Their order is n by n is given to you as 3, so it is 3 by 3 as you can see. It is 3 by 3 as you can see. Another thing provided to us is that these are strictly increasing, that is they are strictly sorted. What do I mean by strictly sorted in case of matrices is that you can see that 1 is smaller than 5, 5 is smaller than 6, 6 is smaller than 8, 8 smaller than 10, 10 smaller than 11, 11 smaller than 15, 15 smaller than 16, 16 smaller than 18, right? So if I jot down in an array, the array would be sorted, right? Similarly, if you see matrix 2, 2 smaller than 5, 4, 4 smaller than 7, 7 smaller than 9, 9 smaller than 10, 10 smaller than 12, 12 smaller than 13, 13 smaller than 16, 16 smaller than 20, right? So one inference I can draw is that the smallest element of, irrespective of what matrix I am talking about, smallest element is present in top left corner, right? In top left corner you can see if they're increasing like this and they're increasing like this, what is the smallest element present? This, correct? You can see from the example also. And the largest element is present on the bottom right corner, right? Largest element is present on bottom right corner, right. Now let's see what does the question ask us. The question asks us to determine the number of pairs AB such that A plus B equals to X. X is also given to us as a input. X is 21 in this case, right? Now the condition is that this A should be from matrix 1 and this B should be from matrix 2 and their sum should be equals to X, right? So we have to be one element from here and another element from here, right? How will we do that? How will we do that? Okay. So to take out the answer, you can see that if I try to pair 1, it will be paired with 20, right? 1 is paired with 20. So one of my answer is 120, right? 5 can be paired with 16. So 516 is another one. 6 can be paired with no one, right? 8 can be paired with 13, I guess. Yeah. So 8 13 will also give me a sum of 21, right? 10 10 requires 21 minus 10, that is 11. Is 11 existing in matrix 2? No. So 10 cannot be paired with anyone. 11 requires 10. That is 21 minus 11 is 10. Is 10 existing? Yeah, 10 is existing. So 10 comma 11 is another. Oh, 11 comma 10, sorry. 11 comma 10 is another pair. 15. 21 minus 15 is 6. Is 6 present? No, sorry. 21 minus 16 is 5. Is 5 present? No. 21 minus 19 is 2. So it's 2 present. Yes. So another pair is 19 comma 2. So our answer is 1, 2, 3, 4, 5. So our correct answer is 5. Now we have to draw some approaches so that we can reach to the final answer. How can we do that? Right? So I say that what was I doing here? I was traversing each element from matrix 1. I was traversing each element from matrix 1 and finding if 21 minus that element is existing in this matrix 2. So what can I do? I can run a loop, right? So for I going from 0 to n minus 1 for rows of matrix 1, for j equals to 0 to n minus 1 for columns of matrix 1, right? Suppose my int x is equals to matrix 1 ij, right. Now I need to find if y, what is y here? Y is equals to x. Sorry, this is let's say a, and this is let's say b. So my b is x minus a. X is the target given to us, that is 21 in this case, right? X is equals to 21, right? So my b is equals to x minus a. So if I find a b in matrix 2, I say that I will increase my count. Suppose I have named a variable count equals to 0 here, right? Initially it is 0 and at last it will have the final answer, right? So now I will have to traverse the matrix 2 again. Not again, for the first time only. Let's say I'm keeping the variables as k going from 0 to and minus 1 for matrix 2 and j going, not J, no, J is already used, L going from 0 to n minus 1 for columns, right? Now, if either I can check on the whole matrix, but I can also check that if B is actually smaller, if B is actually smaller than matrix 2 KL, then there is no way that I can find it above, right? Why? Because the matrix 2 is sorted, right? What I'm saying is, suppose I'm finding 5, right? I'm finding 5. I traverse this is not 5. I traverse this is not 5. I traverse this is not 5. What? 7 is actually greater than 5. 7 is greater than 5, right? So is there any chance that I can find a 5 here? Not possible. Why? Because it is given to us that the matrix is strictly sorted. So I can just optimize it, not optimize it, I can just write that if matrix 2 KL equals to B, in that case count plus plus and this loop, right? And this both the loops, right? Because I found the element, right? Otherwise, else if matrix 2KL is actually greater than B, in that case again break, but without increasing the count, right? Because I cannot find a B now, right? So this is my brute force approach. As usual, we tell the brute force approach first, because that is what the interviewer asks us. So brute force approach, right? What is the time complexity for brute force approach? So you can see running 10 and times, running n times, running n times, running n times. So there is three nested loops inside a outer loop, that is O of, this will be running n times, n times, n times, n times. That is n to the power 4 time complexity. You can see that the problem is actually of easy type. Problem is easy type. And O of n square is asked. You are doubling down, like not doubling down, you are actually squaring the expected time complexity. So it is an inefficient approach. What can we do next? Right? So my optimization technique will be not the optimization in the perfect sense. I will say that I'm making it efficient, right? Efficient. For making it efficient, I can remove these steps somehow. How? How can I remove them? To remove them, I'll say, what is this loop doing? What is this part doing? This part is checking if B, what is B21 minus A, is existing in matrix 2, right? This is the whole purpose of this part, right? We are clear with that. This is the whole purpose, right? We'll say, instead of checking through a loop, what if I run a loop beforehand? I run a loop here, somewhere here, without before this loop. I run a loop here, right? And I take a set and insert all the values of matrix 2 into that set, right? And then I will be using my set to check if B is existing, right? Right? So I don't think I need to write the pseudocode. Once again, I will explain what I have done. I say that I have taken a set here, and using the two loops O of n square time complexity, I have put all the elements inside that set, right? Of matrix 2, matrix 2, right? Of matrix 2. Okay. Then I will be using that set to check if B is existing in that set, right? That just solves the time complexity issue. Yes, it solves the time complexity issue because it will be taking n steps here, n steps here, and let's say that set assumes O of one time. I'm not actually sure what does the findings time of set. You can check it on internet and tell me also. It will enhance my knowledge also. So okay, so I will be using a set and it will be reducing my time complexity, right? But the main concern I have is that the expected time complexity given to us is expected space complexity, sorry, it is given to us is O of 1, right? That is constant. But we are using a set, and set will be storing n square elements, so we are already using a space of O of n square, right? That is what is attacking my ego, let's say ego, and I want to optimize it further. I say, you are a tough question, but I'm tougher than you. I will be optimizing you, optimizing, right? I'll say, let me look at the question once again. Let me look at the question once again. Okay. Let me brainstorm the question. Okay. So if I see the pairs, you can see 120. One was situated here, 20 here, right? Then I moved right. Then I moved right. See, I am drawing the conclusion now. I moved right in matrix 1. I moved right. Went to 5. I went to 5, I saw 16. Now I went right in matrix 1 and I had to go left in matrix 2. I went right in matrix 1 and I had to go left in matrix 2. Why? Because This element plus this element is giving me the output as x, right? Now, if I increase this element, so this is simple mathematics, guys. Like what I'm saying is, if 5 plus 4 is equals to 9, right? Then I'm simply adding that 5 plus 4, and I say plus 1 minus 1 is equals to 9. Now, if I pair this one with this 5, that is 5 plus 1, this minus 1 is automatically paired with 4. So 4 minus 1, right, is equals to 9. So what I'm saying is I'm increasing the left hand, the first term, that is I'm increasing the a term here. So I will have to decrease the b term, right? And so if I'm standing here in the first answer, then I will have to go towards, that is my whole algorithm, right? So what I will be doing is I will be standing here in the first matrix. I will be standing here in the second matrix. That is the top left. That is the smallest element. That is why written them explicitly, right? That was a plot. Okay. So I'm standing here in the first matrix, standing here in the second matrix, right? Now what? Now I'll say if these two elements where I'm standing is, if this element and this element give me a sum of x, that is, if a plus b give me a sum of x, what do? I increase my count, like I keep a count here, no? So I will increase my count, right? Otherwise, two conditions can arise. It is either less than x, it is either more than x. So let's analyze the less than x condition. So, is this element smaller or is this element smaller? Is this element smaller or is this element smaller? See, whenever you encounter less than x, that means you have to increase your this side LHS so as to meet x, right? Whenever you encounter less than x, that is this operator, what do you have to do? This, you have to increase this so as to reach equality, right? Now to increase this, will you move right or will you move left? To increase this term, will you move right or will you move left? Obviously right. Why right? Because right is always increasing, given to us in the question, right? That the matrices are sorted. So which matrix is being traversed in the right direction? Am I wrong? Are we on the same page, right? Are we on the same page? This matrix is being traveled in the right direction, right? So what I will do is, if this condition holds that my a plus b is actually less than x, what will I do? I'll say that I will move my pointer of this matrix towards left, towards right, sorry, right? And similarly, if this is greater than x, if this is greater than x, what will I do? If this is greater than x, that then this side is actually greater than this side, right? So I will have to decrease this side. I will have to decrease this side. And if I'm decreasing this side, what does that signify? If I'm decreasing this side, I will have to decrease something. And what is decreasing? Left side. What is left? Matrix 2, right? Right? I hope you understood. I hope you understood. Let us draw it once again, right? So our matrices are 1, 5, 6. Let me copy down from here. 1, 5, 6, 8, 10, 11, 8, 10, 11, 15, 16, 18, 15, 16, 18. This is my matrix 1, right? This is my matrix 1. What is my another matrix? My another matrix is 2, 4, 7, 2, 4, 7, 9, 10, 12, 9, 10, 12, and last row is 13, 16, 20. 13, 16, 20, right? Right? So my x is 21. I have to find out pairs giving me answer of 21, right? Let me say my count is 0 before traversing, right? And I'm standing here in matrix 1. This is my matrix 1. This is my matrix 2. And I'm standing here in matrix 2, right? Okay. I'll see, is 1 plus 20 given, 1 plus 20's value is 21. Okay. Is 21 matching x? Yes. So count will increase, right? Now, because this has matched, I will move towards right and I will move towards left. So I'm standing at 5. I'm standing at 16. Now 5 plus 16, what is the value? 21 equals to x. So okay, again it comes to 2, it comes here, it comes here, right? No problem, I guess. No problem, I guess, right? 6 plus 13, is it? It is 19. 19 is less than 21, right? 19 is less than 21. So now guess, if I move this pointer here, what will be the sum? 6 plus 12, that is 18. Still less. I have to increase it. If I move this pointer to the here, 6 to 8, what will be my answer? That will be 8 plus 13 gives me 21. Yes? Okay. 3. I am 8, 13 evaluated. Move the pointers. 10 here, 12 here. 10 plus 12, 22. 10 plus 12, 22. 10 plus 12, 22. Okay, greater than means I have to move my move my pointer of the matrix 2, right? So 12 we move to 10. Case is 10 plus 10, right? 10 plus 10 gives me 20. 20 is less than 21, so I will move this pointer. It comes here. It comes here. So now my sum is 11 plus 10, that is 21. I found the correct sum 4, right? I found my correct sum, so I will move both the pointers. It will move to 15. It will move to 9. 15 and 9. 15 plus 9 is, if I sum them up, 24, right? 24 is greater. So if it is greater, I will have to move this because this is reducing part. So 7. 15 plus 7 is 22. 15 plus 7, 22. Again greater. Move it here. 15 plus 4 is 19. Again, it is small. This is small now. So move this pointer. 16. 16 plus 4 is 20. Still small. Move this pointer. 18. 18 plus 2 is 20. So I guess it was 19 here. Let me see it again. And it is 18 here, but I think I copied it 29. Yeah, I took it as 19, guys, while explaining. As you can see, the set is also 19 too. Okay, sorry for my mistake. So it was 19 here in the test case we discussed above. 19 and 2. 19 plus 2 is 21. So again 5, and this will go out of bounds. This will go out of bounds, and our loop is completed. We have won because our answer is matching the corrected value, right? Now, what is the time complexity? What is the time complexity? Oh, great question. So you see, traversing this matrix once, traversing this matrix once, right? Traversing this matrix once, traversing this matrix once. How many elements are present here? N square. How many elements are present here? N square. So you are actually traversing only 2 times n square. 2 times n square, right? No more than that. So time complexity is also O of n square. Space complexity. Have we used any extra space? No, we have not used any extra space. So our space complexity O of 1. Now, for those of you who are not understanding that how will we move, like we can move from here to here, here to here. How will I move from here, this position to this position? So what I will do is for matrix one, let us keep the pointers as R1 and C1 for row one and for row and column, right? So if my column becomes n, if my column becomes n, I will increment my R1 and my column one will become 0. Similarly for this side, this is the flow, right? So if my let us say that the pointers are R2 and C2. So if my column 2 becomes negative, you can see this is the column 0 and this is column minus 1, right? If this column becomes negative, I will turn it to n minus 1, that is this column, n minus 1, and I will decrease the R2, right? Because I'm going upside, right? So I hope that is not a problem right now because coding is actually fun. See, I always say that DSA is all about thinking about the algorithms because code, if you are a good coder, you will convert the algorithm, right? You will convert the algorithm into code. That is a specialty of a code. The coder always gets stuck on algorithm. What should I do here, right? Because that is what matters, right? Coding is actually a cup of tea. You can ask the chat GPT to code for you if you have a correct algorithm, right? Okay. So without wasting any time, let's just code this down. So our int answer is equals to 0. Our row 1 is equals to 0 initially because of top left, right? And our row 2 is equals to n minus 1, and our column 2 is also n minus 1 because we are using bottom right. Let me mark it as comment also here. Top left. Oh, sorry. Let me mark it as here, right? And bottom right. Now what we were doing is, now while, when will this loop end? When will this loop end? This loop was ending when my R2 was actually coming here, because when I will go here, again this will be implemented. My column 1 will become 0 and my R2 will become n. R2 will become n. So R1 will become n. So I will end this when R1 becomes n. That is okay. And similarly here, when R1 becomes negative, right? When R2 becomes negative. So while my R1 is less than n and my R2 is greater than equals to 0, that is it is not negative, what will I do? I will calculate the sum first. So my sum is equals to mat1 of R1 C1 plus mat2 of R2 C2, right? So if my sum is equals to x, my first thing to do is I will increment my answer. That is the important thing. And then I will increment my column 1 and decrement my column 2. I don't think that there is much explanation needed right now because I already explained it. If you don't understand, please go back and watch the video. How did we come to the conclusion to increase the column 1 and decrease the column 2, right? Because I've explained them using this blue marker, right? Okay. Now, else if, what is the case? Sum is less than x. If sum is less than x, increase the increasing pointer. Which one is increasing? The C1 is increasing, the C1 plus plus. Else, what is the case left? Sum is less than x. In that case, C2 minus minus. Now, I will handle the cases of increasing and decreasing the row number. So now, if C1 equals to n, that is, I have reached the end of that particular row. R1 plus plus C1 equals to 0. Any problem, guys? Any problem, guys? No? Okay. Else, not else, only if C2 equals to C2 is actually less than 0. That is minus 1. In that case, R2 minus minus and C2 becomes n minus 1. Right? I don't think there should be any problem in visualizing what is happening. And at last, return your answer. Okay, so let us try to compile and run it. And let us wait because it takes a line. Okay, so output is 4. Expected output is also 4. In the meantime, I would like you to hit the subscribe button. And if you like this video, if you like the algorithm, you can see 87 day streak. And thank you guys for all this love. And we will be in 13 days we will be completing a century, so I want a party from you guys for completing the century. Thank you, have a nice day, and keep coding. Bye, have a nice day.